How you doing? My name is Kevin Bostic, the sole member of group number 5, and my project was the automatic classification of safety-related requirements documents using natural language processing. Okay, so my problem statement is that so one, a little background about myself. I'm a system safety engineer for the Department of War. I've been there for going on 8 years. One of the things that drove this project is that um, I'm currently in school for my master's degree for data analytics engineering, but I had a interest in natural language processing and AI. So long term, even before this class, I wanted to possibly develop some kind of program or some kind of software that could the make our job easier. So as you see in the bullet points, one of the major things that system safety engineers have to do, we're responsible for analyzing mountains of documents, including system requirements documents, capability documents, specifications, a long range of technical documents, and it's our job to go through it, analyze it, and be the one to identify potential safety risks and track that for the program. So I wanted to make use of AI to expedite that process. So I highlight some of the difficulties that we face. Like I said, it requires attentive and manual review of large volume of technical documents. A lot of it is tedious and time consuming. We're also typically under the gun a lot, which means we have a lot of tedious work to do, but very minimal time. And we're also kind of like the health inspectors of the defense acquisition process. So a lot of the times our program managers aren't really on our side. So not only do we have tight windows, but we're also kind of delivering bad news like, hey, you guys can't release this product because of these things that we identified and so forth. So due to the difficulty of our job and the stress, it leads to high turnover. And I think long term, even though I don't address it all in this project, but long term, I think the use of natural language processing would increase our efficiency and overall just help us as a profession. So that's why I'm a little passionate about this project I've done. So, as I just touched on, as far as the problem statement, the objective is to determine whether modern natural language processing techniques can improve the efficiency and accuracy of safety hazard identification. So, to basically summarize it, I wanted to make a model that could be trained on, some of our standard documents, such as the Mill Standard A82, which I'll get into a couple of slides later. And basically, with once the model is trained and ready to go, that you could just upload new documents. So you can upload, a requirements document for a missile or a car or autonomous drone or whatever it is, and you can put it in the model, and the model will be able to extract all of the safety relevant information, which would effectively achieve all the goals I just mentioned. So just going down this slide right here. So the main thing, we want to accurately classify unlabeled requirement statements for safety impact. We want to accurately identify text and technical documents that have safety relevance, and autonomously create an initial assessment of safety related information. So for this project, just some of the technical objectives is to develop a text pre-processing pipeline to clean, tokenize, and prepare technical documents. Create a hazard classification model using TF-IDF feature extractions. Implement that TF-IDF and logistic regression model for safety requirement classifications, and then design and implement a working prototype that accepts technical text and predicts if the text contains safety hazard related information. So the data set I used, so for training the model, I used the military standard 882 Echo, which is basically kind of like the Bible for my profession. A lot of our, yeah, this is the baseline of our profession. So a lot of the safety language that the model needs, it can get from that model. So the data I use for testing the model, I used the NASA Safety Handbook. That was used because it is very similar to the military standard 882 Echo, but it does have its differences. So I wanted to have one document that was kind of cover the same things to see how the model performed on it in comparison to the training model. And then another another source of data that I used for testing the model was the software requirement specifications for a pedestrian backup assist system. So it's basically just it's basically the requirements that went into the design of like your backup assistance in your car. And then last but not least is a manually labeled requirement data set from that same SRS. So obviously I had to extract that SRS document, which is a complete document, but I also extracted a CSV file so I can just pinpoint the requirements. If you're not really too familiar with requirements are pretty specific statements that dictate how a system is designed. So say if for this example, you got the backup assist system. So you might have a requirement saying your system shall initiate auto braking if it's within 5 meters of a detected collision, right? So requirements are basically a document or a table filled with a bunch of shall statements like that that dictates what your system is required to do in order for you to be, to basically meet your objectives. That was kind of long-winded, but ultimately the goal is to train the model that's robust and with safety standards and evaluate whether the model can generalize that information into new data that's used. Okay, this slide goes through the methodology I used for this project. If you look at the left, it basically shows the complete natural language processing pipeline that I used to basically get us from just text documentation to safety classified text. So obviously you got the regular input in the document. That's making sure that the model can read text files, which consider the PDF, either text files or CSV files. We use sentence extraction to basically make sure that the model understands the boundaries of each sentence. Text cleaning is pretty straightforward, getting rid of white spaces, getting rid of headers, footers, references, things that's not supposed to be there. I mean, it's kind of basic stuff. You understand text cleaning. The TF IDF vectorization, that was basically used to identify the unigrams and bigrams and kind of get that good the feature selection process going. At that point, we used the logistic regression model to learn patterns within the data, and that kind of leads to the next point where we figure out, we use logistic regression to be able to get to find the safety probability of each like text or each sentence. And then after that, the completed model will be able to take unrelated documents and be able to extract safety related information out of it. This slide is pretty straightforward. This is just the classification results for the actual training model. So if you look at the confusion matrix on the side, it basically just shows how the model performed. As you can see, the classification results is basically with 77% across the board, and I'll kind of get into that when we get into when I do my model presentation. These are just additional performance indicators showing how the model works across different thresholds. And then I just use precision recall curve because that was basically useful because a lot of this stuff is just actually all of it is just binary classifications between is it safety related or is the sentence not safety related. This slide just shows a quick screenshot of some of the testing outputs that I got. So if you look at the table below, it basically shows that, as I kind of described earlier, the NASA handbook is essentially it is the NASA equivalent of the Mill Standard 882 for my job. So it has a lot of the same. It has a lot of the same talking points, the same safety language. So as you see, that one has the highest percentage of safety sentences, and I don't have the percentage on this table, but I'm pretty sure it shows in the model once I get there. But I believe the percentage is within like 4% of the Mill Standard 882, which is very good, a good indicator for the model. The Bowden SRS document. This is the overall document of the requirements, and that showed about 34% of safety-related sentences, and then the requirements were at 19%. I think the next slide kind of so the next slide shows the error analysis. So how I did the comparison is the initial Mill Standard 882 document, I actually converted it to a CSV file, and every single sentence on that document I had to go through and manually flag each sentence in that document to see if it was safety related or not. So I also did the same thing with the requirements document. So out of those 69 requirements, I went through and manually, just from my own, engineering mind, decided which one were safety. And I used that predetermination to compare it with the prediction. Most of it performed pretty good. The biggest things that seemed to impact some of the errors was that in the requirements document, words like risk and mishap was weighted very heavily in the it was weighted very heavily. So for example, as you see, like in the first example of that table, it says no risk indicates the system has detected obstacles behind the vehicle. So I marked that as non-safety because is a situation basically talking about the risk of nothing being there. But since it says keywords like risk and system and detected, it was flagged as safety. So it's obviously some flaws. I think that would obviously be fixed with a more just a better training model if you was be able to train the model with more information. But that was just some of the limits of this project. I think another which is what I just kind of alluded to, is that my manual classification also caused some. So obviously, looking through 1,300 sentences, I'm human. I probably made some mistakes. Maybe some should have been safety labeled, so some of it is just because the actual source of truth is one has natural human error in it, which is kind of a real aspect of system safety. Then the false negatives mostly stemmed from the operations that was exclusive to that Bowden car thing. So like Mill Standard 882 is really more designed for weapons, explosives, things like that. So a lot of the language as far as like cameras and sensors and pedestrians and things like that, that wasn't in the model. So a lot of things that should have been considered safety, just based on that particular field, like of cars and navigation and stuff wouldn't have been picked up through the Mill Standard 882 Echo. So, lastly, so my conclusion was basically that I concluded that the NLP can be used to expedite the safety identification assessment process by reducing manual review effort, prioritizing safety language in documents, and producing probability scores for more straightforward engineering review. The slide shows a list of accomplishments. I kind of just went through them all. And then I think for future work, I would train a model on more system safety documentation. So instead of just the Mill Standard 882, I could include the NASA. I could include, they might have some automobile guidances out there and all kinds of different fields. So you kind of just build that training model up to be able to better identify stuff. Obviously, using larger labeled data sets. One of the biggest issues I had with this is that, like I said, since what I do is so niche and it's pretty much like a government thing, it's hard to find. I didn't realize how hard it would be to find like system requirements and stuff online. They don't make them publicly available because either, it's military defense stuff or it's proprietary to whoever develops it. And then last, I think obviously my overall goal going forward is to possibly get it integrated into actual system safety engineering workflows, and hopefully one day it could even get to generating in-depth analyses to kind of take that off of our load. So now I'm going to walk through the code for my model. So first, I imported the main libraries that was needed for the project, which were I used regular expression for cleaning. I used pandas for working with the CSV files and the data frames. I used fits to extract text from the PDFs, and then I used scikit-learn for training and evaluating the model. The machine learning components that I used was the TF-IDF vectorizer and logistic regression. Let's go forward to here. So this was the loading function. So this is basically the function I use to load the text files and the PDF files. Fast forward to the class. This is the clean and text function that I use. So essentially, this function removes the extra white space, the reference numbers, figures and tables, and just overall, just the whole purpose of it is just to reduce the noise in the text before passing it into the model. Next is the sentence extraction function. So as you can see, I tried to modularize the overall code. Admittedly, my code, I fixed the code using like my hard skills, but it was a lot less. It wasn't as structured as this, so I did use ChatGPT to help me like structure it into these nice, clean functions instead of just repeating a bunch of code throughout the system. So this function was the sentence extraction function, which basically just split the document into individual sentences, and then I also removed short sentences, dropped duplicates, and then I just applied the cleaning function above to each sentence. So the output in general would just be like a data frame where each row represents each sentence in the document. Next is we go to the loaded. So this is where I loaded the labeled training document. So the labeled data comes from the Mill Standard 882 document. So you'll see later. But throughout the process of me doing this project, I basically converted the PDF into a text file, and then I turned that text file. Then once I extracted that text file, I was able to get a data frame, and then I extracted that into a CSV file, which is where I was able to view all of the sentences in the Mill Standard 882 document and add a column for the safety labels, and then I manually labeled them all. Once I manually labeled them all, I took that CSV file and then loaded it back into the document, which was the main source of the training data. So this is the function I used to load it. Next is the training model in general. This is kind of the guts and glory of the whole thing. So we started by defining X as the clean sentence text and Y is the safety label text. Again, these are variables that was created in some of the other functions beforehand. I used the 80-20 data set split for training and testing. And then I used the stratification so the safety and non-safety labels can stay balanced on both sets. Next, I used the TF IDF. I used the TF IDF vectorization to help the model understand which words was important in each sentence. So as you can see within the code, I used unigrams and bigrams. I also removed the English stop words and I limited the vocabulary to about 1,500 features. Then lastly, in the training model, you have the logistic regression. I used logistic regression because basically logistic regression is just great for binary classifications, and this is essentially just a binary classification method where one is safety sentences, and 0 is non-safety sentences. So moving on to the more functions I made. So you have the prediction function that's right underneath it. This is essentially where we classify each sentence. So after the model was trained, I used the classify sentences function to make predictions on the new data. So this function transforms new sentences using the same TF-IDF vectorizer. Then it predicts two things. It predicts the safety probability and it predicts the predicted label. Next, we have the classifying the full PDF function. So this basically combines the whole workflow that I just went through. So let's move it up so we following along. Yeah, so this one combines the whole workflow together. So it loads the PDF, it extracts the sentences, it classifies them, it exports the results to the CSV file, and it prints the summary information. So it's basically a combination of all the functions. So as you can see, kind of how I mentioned about like modularizing the whole thing, it makes it a lot easier and more repeatable. Then the following functions are just the same thing but for different text files. So you got one for the PDF classification, one for TXT classification, and one for CSV classifications. And this is just how I did the different, like file mediums, so I could do it that way. So after this, we get into the actual model. So here is where we actually train the model. And then you get these what do I keep? Model performance metrics. There we go. I keep stumbling on that. The model performance metrics for the model, which again uses that MIL standard 882 verbiage. Then let's move forward to testing the NASA notebook. So when I test the NASA handbook, as you can see, it basically produces the total sentences and then it produces the predicted safety sentences. And if you look at the output table, it gives me the label and it also gives me the safety probability. So how the classification worked, anything with a probability over 50% is considered a safety, a sentence that contains safety information. So that one is pretty straightforward. The next model shows, the next test shows the Bowden SRS document. And as you can see, that's a smaller document. and it has less safety sentences, but again, it's the same output as the other one, just for another document. So that was me testing it on two documents that was outside of the MIL standard 882 training data. And then lastly was the SRS requirements, which was a part of that SRS document that I handpicked out so I could test how the model worked on actual requirements documents. And this was the results from this. Let's see if I can stop it at a good point. Okay, so as I kind of went through it, so I'm not going to rehash it, but it basically shows. So for this one, I did this data similar to how I did the training data. So I took the CSV file of the requirements that I extracted, and I manually labeled them to, just using my own engineering judgment to identify the safety items, and then I used the predictor to identify which ones were mistakes. So as you can see, we had three. Oh crap! Where you go? We had. Let's go to step pause. We had 35 correct predictions and 29 wrong predictions, and I kind of mentioned it in the other slide on the justification on some of the causes for that. After that, we just have a bunch of visualization models that I used kind of just to support the PowerPoint spreadsheet. So it's not, I don't really want to rehash them. Oh, matter of fact, I actually just noticed. So I actually wanted this one to be in the spreadsheet. I mean, in the PowerPoint, which it hasn't. But so this was basically me. I wanted to show that which were the most important features, and it kind of ties into what I discussed earlier about some of the causes for some of the misidentification. So as you can see, you got mishap, hazard, risk, health, and other things. Those were like had the most impact on the classification. So if it was a sentence that it might not have a safety impact, like the sentence could say there is no mishaps and there's no hazards and there is absolutely no health risk. But since the model picks up that, hey, it's a sentence that say mishap, hazard, and health, it must be safety. So that was just kind of an example on how it can go wrong. So that's why my future work was to get more training data in there. And I think, yeah, all of this was already in the PowerPoint for the most part. So I think this concludes my model. So yeah, I think I already went over the time. I might be 15 minutes over. So thank you, and it's been a pleasure working on this project.